YOLO, short for you. Only Look Once is an advanced computer vision algorithm used for object detection. Imagine you have a photo and you want to know what objects are in it and where they are located. YOLO can do this quickly and accurately. Instead of looking at the image multiple times or regions like some older methods, YOLO looks at the entire image just once. It divides the image into small grids and predicts bounding boxes, like rectangles, around objects within those grids. It also predicts what kind of object each box contains and how confident it is about that prediction. This way, YOLO can detect multiple objects in one go and is really fast, making it perfect for real-time applications like self-driving cars, security cameras, or even just identifying objects in photos on your phone. YOLO has become one of the most popular and powerful tools in the field of artificial intelligence, especially computer vision, making it an exciting algorithm for beginners to learn about and explore. YOLO, short for You Only Look Once, is a groundbreaking convolutional neural network, CNN algorithm designed for real-time object detection in images and videos. One of its key innovations is its ability to process the entire input image in a single pass through the neural network, enabling faster and more efficient performance compared to traditional object detection methods. YOLO achieves this by dividing the input image into a grid of cells and predicting bounding boxes and class probabilities for each grid cell. This approach allows YOLO to detect multiple objects simultaneously, making it highly suitable for applications requiring real-time processing, such as autonomous vehicles and surveillance systems. Over time, YOLO has evolved through various versions, from YOLO v1 to YOLO v9, with each version building upon the previous ones to enhance features such as accuracy, processing speed, and overall performance. These advancements have solidified YOLO as one of the most influential and widely used algorithms in the field of object detection. The YOLO algorithm facilitates efficient and accurate object detection by processing input images through a convolutional neural network, CNN, in a single pass. Initially, the image is forwarded through the CNN, where it undergoes feature extraction to capture essential visual patterns and characteristics. These extracted features are subsequently processed through a series of fully connected layers within the network, which collectively predict both the class labels and bounding box coordinates associated with potential objects present in the image. As part of its approach, YOLO divides the image into a grid of cells, with each cell tasked with predicting bounding boxes and class probabilities for objects contained within its spatial region. For instance, in an image containing a dog and a bicycle, YOLO's grid cells would analyze specific areas and generate predictions for the potential locations of these objects, along with corresponding class probabilities. Following this prediction phase, YOLO employs a post-processing algorithm to filter and refine the predicted bounding boxes. This algorithm ensures that redundant detections are eliminated and only the most confident predictions are retained, enhancing the accuracy of the final output. Object detection is a fundamental task in computer vision that involves identifying and locating objects within an image or video. This process goes beyond simple image classification, as it not only predicts the presence of objects, but also provides bounding boxes around each detected object along with their corresponding class labels, enabling precise localization within the scene. There are two main approaches to object detection: traditional computer vision-based techniques and deep learning-based methods. Traditional computer vision techniques rely on handcrafted features and algorithms, such as Haar cascades or histogram of oriented gradients, HOG, combined with classifiers like support vector machines, SVM, or decision trees. In contrast, deep learning-based approaches leverage convolutional neural networks, CNNs, to automatically learn features from raw pixel data, leading to more accurate and robust object detection. Popular deep learning algorithms for object detection include YOLO, you only look once, faster RCNN, and SSD, single-shot multi-box detector. Object detection finds applications across various domains, including autonomous vehicles, surveillance systems, healthcare, such as medical imaging, and robotics. For instance, in autonomous vehicles, object detection is crucial for identifying pedestrians, vehicles, and obstacles on the road, while in surveillance systems, it helps in monitoring security cameras by detecting and tracking suspicious activities or intruders in real time. Object classification is a fundamental task in computer vision, focusing on identifying the primary object category present in an image or video frame. Unlike object detection, which provides both object identification and spatial localization, object classification solely determines the dominant object class without spatial information. Typically accomplished through training machine learning models like convolutional neural networks, CNNs, on labeled datasets, object classification entails learning to extract relevant features from input images and mapping them to specific object categories. This process finds diverse applications, including image tagging, content-based image retrieval, visual search engines, and product recognition in e-commerce. For example, an object classification algorithm trained on a dataset of pet images could accurately classify an image containing a cat as belonging to the cat category, regardless of its position within the image. Similarly, it could determine the predominant animal class in images featuring both cats and dogs, facilitating various applications requiring object categorization. In the realms of both machine learning, ML, and deep learning, DL, a dataset serves as the foundational building block for model training, validation, and testing. A dataset typically consists of a collection of structured or unstructured data points, each comprising input features and corresponding labels or targets. These features represent the attributes or characteristics of the data, while labels denote the desired outputs or predictions. In supervised learning tasks, datasets contain paired input-output examples, allowing models to learn patterns and relationships between features and labels. In addition to features and labels, datasets may also include annotations, providing additional context or ground truth information for specific tasks such as object detection or segmentation in DL. Proper dataset preparation, including data cleaning, pre-processing, and splitting into training, validation, and test sets, is essential for ensuring the effectiveness and generalization capability of ML and DL models. Ultimately, the quality and diversity of the dataset significantly impact the performance and reliability of the trained models in various real-world applications. The COCO, Common Objects in Context, dataset stands as a foundational resource in computer vision, offering a vast collection of over 330,000 images spanning 80 distinct object categories. Each image within COCO is meticulously annotated with bounding boxes and class labels, providing detailed information crucial for object detection tasks. The dataset covers a diverse array of common objects found in everyday scenes, ranging from people and animals to vehicles and household items. Beyond its broad coverage, COCO offers task-specific subsets tailored for various computer vision tasks, including image captioning, where images are paired with human-generated descriptions. Additionally, COCO fosters innovation through challenges and competitions that drive advancements in object recognition algorithms. Its accessibility for research purposes, coupled with support in popular deep learning frameworks, positions COCO as a cornerstone resource for training, evaluating, and benchmarking computer vision models, ultimately advancing the capabilities of visual perception systems. The YOLO, you only look once, architecture revolutionizes object detection by employing a single convolutional neural network, CNN, to simultaneously localize and classify objects within images. This unified approach divides the image into an XS grid, with each grid cell responsible for predicting bounding boxes and class probabilities for objects within its spatial region. During the bounding box recognition process, Yolo first divides the input image into the grid, then predicts a predetermined number of bounding boxes, B, and confidence scores for each box within every grid cell. Additionally, each grid cell estimates conditional class probabilities, C, using softmax activation, allowing the model to assign probabilities to each class for every predicted bounding box. This streamlined architecture and bounding box recognition process enable Yolo to achieve real-time object detection with both speed and accuracy, making it a widely adopted solution for various computer vision tasks. To run the Yolo model on platforms like Kaggle or Colab, you'll first need to set up your environment by creating a new notebook and ensuring GPU acceleration is enabled for faster computation. Next, clone the Yolo repository from GitHub using the git clone command and download the pre-trained weights necessary for inference with the wget command. Prepare your input data, whether it's images or videos containing the objects you want to detect, and ensure it's accessible within your notebook environment. Then, use the Yolo 7 script detect.py to run inference on your input data, specifying parameters such as the path to the pre-trained weights, confidence threshold, image size, and source data. After running inference, analyze the results to understand the detected objects, and optionally visualize the output using image processing libraries. Finally, download the output files containing the annotated images or videos with bounding boxes and class labels for further analysis or use. Adjust the commands and parameters as needed for your specific use case and input data. Congratulations on reaching another milestone in your journey to master one of the most exciting fields in artificial intelligence. Throughout this course, you've explored the world of Yolo, discovering its incredible potential and practical uses across various areas. From understanding the basics to diving into more advanced concepts, you've navigated the Yolo landscape with curiosity and determination. But mastering Yolo isn't just about learning. It's about applying your knowledge in real-world scenarios. As you continue your journey, keep experimenting and solving problems. Remember, mastering Yolo is both thrilling and rewarding, and your dedication will lead to success in this exciting field.